So I'm going to tell you a little bit about some of the thinking I've been doing about using radar data for geologic interpretation purposes. One of the things that really prompted this was the A3GT proposals, which were, not particularly fun process, but nonetheless, they did get me to dig into the pixels and think about how we might design traverses. So if you go to the next slide, I've talked to many of you already in various meetings about how we've been working on reprocessing the data that's in the PDFs from MiniRF monostatic data products. Basically, all of the data have been reprocessed into a lunar reference frame consistent with LOLA and the SLDEM at lower latitudes. LOLA at high latitudes in the poles, like where Artemis is, and SLDEM at lower latitudes. And so that orthorectification means we can then use it in the context of other data, which is obviously really important. If you go to the next slide, I show what one of the things you can do with this is once we know where the data is with reference to the topography, we can then correct the radar results for the illumination effects. So the middle colorful CPR diagram there has a lot of red pixels on the inside of the crater where it's the illumination is coming from the right. And if you take into account the fact that those were seeing very, very high incidence angles, that's the dominant reason why those have high CPR. It's not related to the material properties of the surface or anything to do with how the radar wave would interact with the similar material on flat ground, but it's just geometric. It's basically how the incidence angle of the radar wave is intersecting the topography. And so if you see on the left there, that rainbow cloud of points, you can take the trend for how local incidence angle relates to CPR, and if you remove that, you can get what I call the delta CPR, or the CPR that's taking into account the incidence angles. And basically, that's the residual of CPR if it was observed at a constant incidence angle. And we've done the similar thing with radar power, or S1. So if you go to the next slide, I just have a comparison of what one of these the south pole of the moon looks like in CPR, with just averaging a whole lot of collects, taking at different illumination geometries with the delta CPR, and hopefully it instantly jumps out to you that the delta CPR product is more useful for recognizing regional scale geologic trends. So if you go to the next slide, I show delta S1 as well, and what we've been doing is trying to take these new products and use them for regional geologic characterization, and also for specific local scale analyses, which we'll talk about as we get towards the end of this presentation. So if you go to the next slide, I wanted to point out a few things specifically related to what you can see in this Delta S1 product. One is that now putting these Artemis landing sites on board, the array from Tycho goes straight through the Howarth and Connecting Ridge landing sites, which have been pointed out now many times by other authors, but it's really neat in the radar. It stands out really prominently. So if you flip back to the previous slide and track that black line in your mind, you can probably see it. Yeah, so it's a yellow line that crosses from the top of the diagram down through the middle. Yeah, that's perfect. Thanks so much. Next slide again. The other thing that stands out in Delta S1 is that the Mons Mouton region is a real anomaly here. It's blue, or lower radar reflectivity. The Faustini landing site has this really prominent crater sitting right in the middle of it that makes higher S1 products there. And also, you may notice that all the PSRs of the classic craters, Shoemaker, Faustini, Hayworth here, are all higher in Delta S1, which we currently attribute to a change in the regolith properties, regolith radar properties, due to just having lower temperatures. But it could also be a combination of that and some change to the porosity or density as well. We have to work that out still. If you go to the next slide, I have some additional. Oh yeah, I put in this really nice zoom in of the ray crossing Hayworth, just to give you a sense, like of how that might affect the geology if we go explore there. It's basically the dominant feature in that landing site, and the radar really shows that, and it's not as evident in optical. If you go to the next slide, I have a similar set of points about delta CPR. The main things that stand out here really are that Montana is like this red anomaly. It's high CPR. And we know it's also low S1. And the combination of those two things have led us to interpret it as potentially an area of higher porosity, maybe by 10 to 20% than sort of typical highlands terrain. It'll be really interesting to see whether that plays out correctly with Viper drills and next year. If you go to the next slide, I'm going to start talking now in more detail about the A3GT study area, which I hope some of you have great familiarity with from your own work in this place, I guess in April, March of this year. That circular region there was a 2-kilometer radius area that was designed as the place where we would land. And you can see that it overlaps a fairly fresh crater on its margin. And the radar really shows nicely the ejecta blanket of that crater. So if you flip to the next slide, I have a few examples of how I used this radar product when I was thinking about this location. One is I went through and basically looked at all the places where there were bright pixels or pixels that stood out from sort of background highlands terrain, because they tended to correlate well with either areas that were rocky or were fresh impact craters. And so it was a good way of distinguishing craters that were fresh from craters that weren't fresh without having a whole lot of digging to do in the data set. And so on the left here, we have that S1 product again. And on the right, it's the LROC NAC. And you can see this is a rocky crater sitting in the ejecta of that larger impact crater. I should say for this Malapert collect, I sent around, I think, to all the teams who were working on this, the Delta S1 product, and it was combined from 42 overlapping collects. So because of that, it's averaging in a lot of different products, and it's computed at 15 meters per pixel. And so it really is fairly high fidelity for the radar reflectivity product. It's not very, there's not very much noise that persists in this from speckle noise or anything else. And so where we have lots of these overlapping collects near the poles in many of the Artemis landing sites, it's going to be a really useful product. If you go to the next slide, this is just another example of a hot pixel where there's a rock. Perhaps not so interesting, but it is a way that you can go and then find things that are cool that you might not see quickly in LROC NAC. If you go to the next slide.
Just over 2 minutes.
Yeah. I think this is probably the part where the real utility just stands out. So I've stretched this S1 image on the left. And at least to me, the highlands are almost all one unit on the moon, right? So it's really often very tricky to figure out where you would put these diffuse contacts that probably exist in many places where they're all regolith covered. But because the radar sees through the upper surface and is also sensitive to changes in grain size variation, the ejecta extent from this crater stands out dramatically in the radar image here. And so I drew what I would call a diffuse contact between where you would walk on ejecta here and where you wouldn't have as much ejecta. And it really highlights how asymmetric it is. And if you flip to the next slide, I just zoomed out a little bit more. Just show this off again. The asymmetry here is due to the crater forming on this 15-degree slope that we were going to put the astronauts on to traverse. And there's dramatically more ejecta that went downslope than upslope. And so without the radar, I'm not sure it would have been easy to recognize how asymmetric this is and to know where you would cross into the ejecta unit. And so I listed as takeaways for this talk that the radar products are really useful for identifying fresh craters and for looking where there might be rocks on the surface that you might want to then go verify in LROC NAC. But it's also useful for tracking the boundaries of ejecta and other geologic boundaries that are not necessarily obvious in any other data set. And so that's what I brought today. I stuck at the end of the presentation for the organizers just a list of my answers to the questions they wanted us to answer, but we can get into that more as we discuss these presentations. So thanks.